Welcome to our deep dive. Today we're jumping straight into a paper that honestly feels like it resets the bar for efficient LLM agents. It's called AGENTFLOW. In the Flow Agentic System Optimization for Effective Planning and Tool Use.
Yeah, this one tackles a really core problem we're seeing. When you try to build agents for complex tasks, things that take multiple steps, the standard methods start to wobble. They train this one big monolithic policy, and it just gets unstable, kind of brittle when the task gets long.
Right, and AGENTFLOW comes in with, a much more surgical approach, a trainable agentic framework. It actually decomposes the work. You've got 4 specialized parts: a planner, an executor, a verifier, and a generator, and they're all coordinated through this evolving memory system.
And the real magic, I think, is how they train it. This new algorithm, flow-based group refined policy optimization, let's call it FlowGRPO, it's easier.
Okay, FlowGRPO.
It lets them optimize the key planning part, the action planner, on policy. So it's learning directly from its experience during the multi-step task. That's pretty novel.
And the headline result, the thing you really need to jot down, is that AGENTFLOW, using a relatively small 7 billion parameter model, Qwen 2.5 specifically.
Yeah, just 7B.
It didn't just hang with the big guys. It consistently beat larger, specialized models. And even giants like GPT-4o, which is around 200 billion parameters, beat it across 10 different reasoning benchmarks.
It's a huge deal. Shows that smart training can really punch above its weight class in terms of parameter count.
Absolutely. Targeted training trumping raw scale. Okay, let's get into the weeds.
So let's start with maybe why the agents you might be building now, the multi-turn ones, sometimes just fall over in production. The standard way, tool-integrated reasoning, or TIR, it trains one massive policy.
Right, you ask that single model to do everything. Figure out the plan, decide if it needs a tool, pick the right tool, make sure the API call is formatted perfectly, all in one go.
Exactly. And you can imagine asking one thing to juggle all that, especially when the conversation history, the context, keeps growing. It just doesn't scale well.
That's the pain point, isn't it? The exploding context window. And the training just becomes incredibly unstable as the reasoning chain gets longer and longer.
Precisely. You get instability, especially when, say, a tool gives unexpected feedback. And then trying to make it generalized to slightly different tasks, forget it. It becomes incredibly brittle. It's a known ceiling for these monolithic designs in the agent world.
Which is why Agentic Systems always looked promising, at least on paper. Break it down, have a planner module, maybe a critic or verifier module. Seems more robust, like a team of specialists.
It does feel more intuitive. But the catch, until now really, is that most of these agentic systems haven't been trainable in the same way. They're often training free.
Meaning they rely on prompts or hard-coded rules.
Yeah, static prompts, maybe some handcrafted logic to stitch the modules together. But if a tool fails unexpectedly, or the environment shifts, that fixed logic can't really adapt, can it?
No, it just breaks.
That's the decoupling. They struggle with sparse rewards. You only know if the whole multi-step task worked at the very end, and they're just not resilient to the messiness of real-world execution.
So if your agent hits an error from a Google search API, or a Python script throws an exception and it just gives up or gets stuck in a loop, that's that brittle adaptation we're talking about.
Exactly, and that's what AGENTFLOW aims to fix. By making the planning part learn how to recover, how to be resilient, directly in the flow of those dynamic interactions and potential failures.
Okay, so let's dig into the structure. 4 modules. It sounds maybe a little complex. Why 4? Is there a risk of over-engineering it?
It might seem like it at first glance, but the way they've decomposed it is actually, quote, strategic. Each module tackles a specific weakness of the monolithic approach. They frame the whole thing as a Markov decision process, where the state is this evolving memory.
Makes sense. So walk us through the 4 components.
Right. So first, you have the action planner. This is the heart, the trainable policy, 2p38. Its job is high-level strategy. It figures out the next sub-goal, chooses which tool to use, like the Python coder or Google search, or maybe just the base LLM, and pulls relevant info from the memory.
Okay, planner sets the course.
Then comes the tool executor.
Yeah.
This one's pretty straightforward. It just takes the planner's instruction and calls the chosen tool. It then passes back whatever the tool returns, the observation. Let's call it Tathelers. They use 5 main tools here. The base LLM itself for generation, a Python interpreter, Google search, Wikipedia search, and a general web search.
Got it. Planner decides, executor acts, what's next?
The execution verifier. This is super important. It's like the quality control step, the critic. It looks at the tool's output, $2, and asks 2 key questions. First, did the tool execution actually work? Was it valid? Second, based on everything we've done so far, stored in memory, do we have enough information to answer the original question? It outputs a signal, $5.
And that signal determines if we continue or stop.
Exactly. If VT$ says keep going, we loop back to the planner. If it says we're done, VT$1, then it triggers the final module, the solution generator. This module takes everything gathered in memory and synthesizes the final answer.
Okay, planner, executor, verifier, generator, PEVG cycle. But you mentioned the evolving memory M tying it all together. Context management is like the bane of agent development. How does the memory help here? What's the clever part?
The memory M is really the backbone that stops that context window explosion we talked about. It's not just a raw transcript. It's a deterministic structured record. It logs the states, the planner's actions, the tool results, the verifier signals, everything.
Structured how?
Think key value pairs or a defined schema. Because it's structured, you get really transparent tracking of what happened. You can see the reasoning path. And crucially, it allows for controlled context growth. The planner doesn't get the entire ever-growing history dumped on it.
So it pulls only what it needs.
Precisely. The planner has a mechanism to retrieve only the relevant pieces from this structured memory. That bounds the context fed back into the LLM, which is a massive advantage over monolithic systems constantly battling huge context windows.
Right, this is where it gets really interesting for me. Building the modular structure is one thing, but training that planner policy inside this dynamic loop, that's the classic reinforcement learning challenge, isn't it? Long horizons, sparse rewards. How do you know which step contributed to success when the only feedback is correct or incorrect, maybe 10 steps later? How does FlowGRPO actually assign credit?
That's the core innovation, the elegant bit. Flow-GRPO basically transforms this super complex multi-turn RL problem into something much more manageable, a sequence of effectively single-turn policy updates.
How does it manage that transformation?
Well, think about standard RL in this setting. Trying to calculate some intermediate reward at step 3 based on a final outcome at step 10 is notoriously hard. It adds so much noise, so much variance. Flow-GRPO sidesteps that completely.
Okay, avoids intermediate rewards. So how does it use that final 0 or 1, the success or failure signal?
It takes that single final outcome reward, let's call it a tau for the whole trajectory tau, where R is 1 for success, 0 for failure, and it does something simple but powerful. It broadcasts that exact same final reward signal back to every single planning decision, deal that was made within that trajectory.
Wait, so every single step gets the same final grade. If the whole thing worked, every step gets an A, and if it failed, every step gets an F.
Essentially, yes. Instead of trying to figure out complex partial credit, it says, look, this sequence of actions led to success, so every action in that sequence gets positive reinforcement, or conversely, this sequence failed, so every action shares the negative reinforcement. It's a blunt instrument, maybe, but it strongly aligns every local decision the planner makes with the overall global goal of succeeding at the task.
Okay, but doesn't that introduce a lot of noise? A single bad step could poison the whole trajectory, but all steps get blamed.
That's where the GRPO part comes in group your fine policy optimization. To stabilize things, they use group normalized advantages. They look at a batch of trajectories, a group, and normalize the rewards within that group. This helps smooth out the variance and makes the learning process much more robust, even with that sparse broadcasted reward signal.
So group normalization handles the noise. And the key insight here is that this training has to happen on policy in the flow.
Absolutely non-negotiable, and they proved it quite dramatically. They tried training the planner using standard supervised fine-tuning, SFT, just showing it examples of successful trajectories and asking it to imitate them offline.
How did that go?
Total collapse. Performance absolutely tanked. They saw an average accuracy drop of 19% compared even to just using the frozen, untuned baseline planner.
Wow, 19% worse just by trying offline imitation.
Yeah. It's strong evidence that static imitation just doesn't cut it. The planner needs to learn by interacting with the dynamic system, seeing how his actions influence the tool calls, the verifier feedback, the memory state in real time. You have to train it on the exact kind of messy, interactive dynamics it will face during actual use. Offline SFT just can't capture that.
Okay, let's talk results, because this is where the rubber meets the road. A 7B parameter model, Quen 2.57B, going up against specialized models, and even GPT-4o. Why does this approach work so well? How does targeted training on this modular setup beat like 30 times the parameters?
I think it comes down to efficiency and specialization. That 7B model isn't wasting its capacity trying to simultaneously be a great writer, a great coder, and a great planner, all within one monolithic structure. It has a dedicated planner module optimized purely for strategic decision-making using FlowGRPO, and it leverages external tools for the heavy lifting like complex calculations or web searches.
So it's focusing its parameters smartly.
Exactly. And the results really bear that out. Across different types of tasks, the gains were pretty substantial. On search-heavy tasks, like needing to find info across multiple documents or hops.
Like 2-wiki multi-hop or IRC.
Right. On those, AGENTFLOW showed an average accuracy gain of almost 15% compared to the best competing baseline. That's a big jump.
15%. Okay. What about more complex agent tasks?
On GAA, which is designed to mimic complex, real-world assistant tasks, they saw a 14% gain over the top baseline. And in mathematical reasoning.
Always a tricky one for LLMs.
Yeah, very tricky. They saw gains of 14.5% there, too. Even in scientific reasoning, where baselines are already pretty strong, they got a solid 4.1% improvement.
Those are consistent, significant gains across the board. But the comparison everyone will talk about is GPT-4o, a 7B model versus a roughly 200B parameter beast. You're saying the 7B AGENTFLOW won.
Across all the domains they tested, yes. The smaller, specialized AGENTFLOW outperformed GPT-4o. The advantage ranged from about 8.2% on the search tasks up to a, frankly, staggering 18.0% improvement on the math benchmarks.
18% better on math from a model almost 30 times smaller.
It really drives home the point that architecture and smart targeted reinforcement learning are becoming incredibly powerful levers for performance. It's not just about scaling model size anymore.
Okay, that's scaling model size. What about scaling task complexity? Did they test if AGENTFLOW could handle longer, more complex reasoning chains gracefully?
They did. They looked at performance when they increased the maximum number of allowed interaction turns, Tmax, from 3 up to 10.
And what happened? Did it get stuck in loops, or did it actually use the extra turns effectively?
It used them effectively. Performance consistently went up across the challenging tasks like 2-wiki and GAIA as Tmax increased. This is really important because it shows the FlowGRPO training teaches the planner to use those extra steps for better refinement, to dig deeper, rather than just repeating itself or getting lost, which is a huge risk when you give an untuned agent more rope.
So the on-policy training clearly works for the final score. But can we peek inside? What did the planner actually learn to do better? What changed in its behavior, especially around using tools?
That's one of the really cool parts of the analysis. They looked at tool calling reliability. How often does the planner generate a badly formatted request for a tool, like mess up JSON or wrong arguments?
Oh yeah, that's a constant headache in practice.
Well, the error rate for tool calling dropped significantly during FlowGRPO training. On the GAIA benchmark, it decreased by up to 28.4%. That's huge. It shows the planner isn't just learning which tool to pick, but also the really crucial practical skill of how to call it correctly.
Wow, a 28% reduction in just calling the tool wrong. That's a massive gain in operational stability, something you don't always see reflected in just the final accuracy number.
Absolutely. And then there's the adaptive tool selection. The trained planner got smarter about which tool to use depending on the task.
How so?
Okay, take the 2-wiki task. It needs broad, multi-hop knowledge retrieval. On that task, the FlowGRPO trained planner significantly increased its use of the general Google search tool by about 42%. It learned it needed a wide net.
Makes sense.
But now look at MedQA, the medical question answering task. It's much more specialized. Here, the trained planner learned to drastically reduce its reliance on general Google search usage, dropped from over 66% down to around 11%.
And what did it use instead?
It shifted heavily towards more specialized tools, particularly Wikipedia search. Usage there jumped up to nearly 60%. It learned to dynamically allocate its information gathering resources based on the specific demands of the query. That's strategic intelligence emerging from the training.
That's really impressive adaptation. Let's talk about that self-correction example they highlighted from GAIA, the one about calculating something with a Tropicos ID and an ISBN 10. We've all been there, debugging an agent stuck in a code execution loop. It's maddening.
Oh yeah. So in the failure case, this was the baseline agent without FlowGRPO tuning. It did manage to retrieve some initial data correctly, but then it tried to use the Python coder tool and hit an error. Name ISBN is not defined, a common kind of coding mistake.
And the untuned agent just kept trying the same wrong thing.
Exactly. It got completely stuck. It called the Python tool with the same faulty command 7 consecutive times.
Yep.
Steps 3 through 9 were just repeated failures. It couldn't figure out how to change its approach.
Like banging its head against the wall, the definition of insanity, right? Doing the same thing over and over.
Pretty much. But the agent trained with FlowGRPO showed real resilience. It also hit an error with the Python coder on its first try. But critically, it learned from that failure signal provided by the verifier.
So what did it do differently?
In the very next step, turn 4, the planner didn't just repeat the command, it spontaneously adapted. It modified the Python command structure, presumably based on the error message, tried again, and this time it successfully computed the required check digit. It found the right answer in just 4 steps total.
That ability to pivot, to learn from an error within the flow and try a different strategy, that's the core value proposition here, isn't it? That's what the on-policy RL buys you.
Precisely. That trained resilience is what makes this approach so powerful, compared to static or imitation-based methods. Hashtag tag outro.
Wow. Okay, this has been a fantastic deep dive. So boiling it down, the 3 really key takeaways seem to be, first, the AgentFlow architecture itself with its modular design and that crucial structured memory system.
Yep, the PEVG cycle plus smart memory.
Second, the Flow-GRPO optimization algorithm, solving that really tough sparse reward, long horizon credit assignment problem by broadcasting the final outcome back to every step.
And doing it on policy, which is key.
And third, the undeniable empirical results. A small 7B parameter model trained this way, decisively outperforming much larger proprietary models like GPT-4o across a whole range of tasks.
Yeah, the evidence is pretty compelling. I think the paper really sends a strong message to the field. Monolithic models, while powerful, seem to be hitting a functional feeling for complex, dynamic agentic tasks.
So the path forward is modular.
It looks like modular decomposition combined with this kind of targeted on-policy training within the live interaction loop is where we need to go for efficiency and, importantly, resilience in our agents.
Okay, so here's the final provocative thought for you, the listener, to mull over. AgentFlow successfully used FlowGRPO to optimize the planner module, the decision maker. We saw how effective that was.
Right, optimizing the what to do next part.
So what happens if we take that same Flow-GRPO algorithm, that same outcome-based reward broadcasting, and apply it not just to the planner, but also to optimize, say, the execution verifier module?
Training the critic itself based on whether the whole task ultimately succeeded or failed.
Exactly. How much more stable, how much more robust and reliable could the entire system become if the module responsible for judging progress and tool success is also learning and adapting directly from the final outcome?
That's a really interesting question. It suggests the agent optimization game. Well, it might have only just begun. Optimizing one module yields these results. What about optimizing multiple interacting modules with the same principles? Lots to explore there.